Hello. Okay, we're going to get started again. So this is the last talk of the conference, actually. So it's been great. Yeah. Two important announcements. First of all the speakers should please go see Kat at the registration desk before we all clear out of here. And the second important announcement is just a warning that the mysterious bag of Doritos on the table outside is not an official conference-provided snack. So we suspect it's a tangy and crunchy honey trap. So with that, I'd like to introduce Richard Johnson.
Hello, yes, I'm Richard Johnson, and today my talk is Ghost Speed Tracer. Just to start off, I'm honored to be speaking here at the 10th anniversary of Recon. This is the third time in the last 4 years I've been here. You might have seen some of my earlier talks on concolic execution and other high-speed, high-performance fuzzing. And this talk, we're going to drill a little bit further down into the tracing engine design, as well as some of the background that has taken us from 10 years ago, early explorations into evolutionary testing and genetic algorithms as applied to fuzzing, and how we've arrived at modern toolkits like Amercian Fuzzy Lop and things like that. So I'm a research manager for a team at Cisco, and by way of SourceFire, several of our team members are in the audience, and hopefully you guys have had a chance to talk to them. Generally speaking, we work on finding vulns and writing tools to help assist with that. I do want to give a special shout out to a collaborator of ours who's also part of Talos, but not my team, Andrea Alivi. He's been really essential in helping put together some of the Windows driver side of this talk. So at the beginning, we're just going to do a brief overview of how tracing can be applied in your day-to-day. We'll probably skim through some of this early stuff fairly quickly because I've added a substantial amount of information to this talk since the first run. But then we'll go into guided fuzzing, kind of which approaches to guided fuzzing had merit along the way in the last 10 years, what attributes have actually influenced where we are today, why we have things like high-performance feedback signal-oriented mutation fuzzing that's highly effective, and then specifically talk about engines such as binary translation and the hardware tracing engines that are available in your CPUs, specifically Intel. So the goal is to get an idea of what attributes are useful, and if you're going to go write your own fuzzers, what things to keep in mind that we can learn from past work of the giants that we stand on, and then figure out what things are remaining to be optimized, and how can we push the technology forward continually. And then finally unlocking this new feature set in the Intel processors as of Broadwell and Skylake. It's a completely new hardware tracing mode that recently was just added to the Linux kernel, but to date has not really had support on Windows. And it's a very efficient engine, so we'll get into details on that later. But as far as applications for doing tracing, obviously in software engineering, you can use it for unit testing, performance monitoring. It's useful in malware analysis for unpacking and behavioral analysis, automated sandboxes, things like that. We saw Microsoft give away $250,000 for mitigations based upon LBR tracing engines. And also memory safety checkers oftentimes also do tracing for data flow and things like that. But in software security, we're mostly interested in applying tracing to doing things like corpus distillation so that you can observe whether or not the inputs that you might be using in fuzz testing are useful, and trying to reach that minimal set so that you reduce your total byte space down to things that will be effective if you're going to go ahead and randomly mutate them. And then, and more recently, getting into guided fuzzing and being able to provide a feedback signal during the testing process. And of course, in post-crash analysis, tracing will allow you to do things like recover data flow and try to automate some of the root cause analysis of the crashes that are occurring. And we've released tools previously that did some things like that. In my talk a couple years ago, that was about the Sage clone, and then some other tools written on top of BAP that do slicing and forward symbolic execution, things like that. And then most recently, interactive debugging. GDB now has some hooks into the Linux perf subsystem so that you can turn on some of the tracing features that are available. And so when it comes time to do your crash analysis, you have a trace log there. So if you have a corrupted stack, for example, you can simply reference the trace, which is a complete recording. And so those are just general applications. A lot of people have written tracing engines that are kind of a higher level hooking style tracing at function levels and API level things. Last year, Alex's talk was really amazing on the esoteric hooking engines. It was fantastic if you haven't seen it. Obviously, his talk today was also great. But it influenced me quite a bit, and actually I wrote a hooking engine that is built upon the Nirvana, or upon the app verifier stuff to help launch some of this trace engine logic as well. But in general, we know there's things like the ptrace interface, debug engine. I mean, this is recon, so I don't have to go into detail there. In binary instrumentation, we see things like compiler plugins that are efficiently able to interleave callbacks into functions or blocks via GCC or LLVM. And then we've also probably been familiar with things like Valgrind over the days, Dynamo Rio, Pin, more recently Dynast. We released some tools based upon that, which is static rewriting. And we'll go into detail about the benefits and kind of the internal design of some of these engines so that we can understand why is Pin and Dynamo Rio, what's the performance differentials, what were the decisions that were made that determine whether or not a DBI is actually performant or not. And then recently we have new engines based on like V8, like Frida, and I'm sure there's others that, I'm not going to enumerate them all, but tracing engines are ubiquitous and available and useful and, something to be interested in. But it's also important when you go to pick a tracing engine that you're picking one that's kind of tuned towards the application that you're looking to supply. So besides the software-oriented DBI engines, there's native hardware support and tracing going all the way back to the Pentium 4 on x86. And even before that, if you count the single step and breakpoints. But I'm sure that we've all done a little bit of interactive debugging, so we've seen single steps and breakpoints. Maybe you've seen back in the process stalker days, or even at CanSec this year, discussion about the branch trace flag, which is just a simple couple of bits that turn a single step into an actual branch step. Last branch record is a functionality in the CPU that is essentially a set of spill registers that allow you to, whenever you do a branch into a call or a branch within your logic, it will actually pop the last branch location into a set of dedicated registers. Branch trace store is an extension on that, and that will take those registers that are and push them into a cache, which then you can retrieve later as well. And then the latest things that I'm going to talk about is Intel processor trace. And then there's ARM core site, which was discussed a bit the other day. So before we get really deep into the internal architecture of tracing engines, let's just take a kind of walk through guided fuzzing and how we've got to where we are today. Can I get a quick raise of hands? If you guys, anybody in the audience has used Amercian Fuzzy Lop or honggfuzz or Jared DeMott's EFS back in the day, anything like that? We got maybe a quarter? Okay. So evolutionary testing was originally white box testing done on source code, typically for high critical systems that needed safety against failure, including denial of service and things like that. And the source code allowed them to do a prior analysis of the graph and do things like static analysis that determined areas that might lead to exceptional conditions. And then they would use evolutionary testing to try to craft inputs that would get you to those locations. This allowed them to define a fitness function that was essentially distance from a targeted area in the graph. So if you already know where you want to go in a graph, you can do a trace and record where you visit in this particular iteration and determine whether or not you got close to where you're trying to land. Now, when we do vulnerability research, we don't necessarily know where the bugs are yet, so this is just how this influenced the later development of fuzz testing. But ultimately, it was still difficult to define properties that tell you how to traverse graph edges and get to the locations that you're interested in. And the applications were not really security specific in the sense of like finding vulns that you can exploit or anything like that. But it was the early generation, mostly government, avionics, some automotive, things like that. So Bringing it into the fuzzing realm, what we're trying to do is apply this concept of having an evaluation of fitness or an evaluation of where you went in a graph over your execution to determine if it was better than your last mutation. Are you visiting new areas of the graph, essentially? So in the concept of evolutionary testing, you have a sample set. That's your pool of samples. You have operations that you perform on your samples, which tend to be, just like in genetics, random mutations and crossovers. And then you have a way to evaluate whether or not those random mutations or crossovers were actually fit to continue executing in that function, which in this case, the function is generating inputs that will eventually lead to crashes or discover more code coverage ultimately. So the first time this was discussed in public was as applied to security testing for finding vulns was at Black Hat in 2006, and Embleton and Sparks talked about a tool called Sidewinder. And it was actually really cool. They took, I think their approach was pretty intelligent, and they took a Markov process, which is a way to weight a graph for essentially likelihood for visiting that path over time. And so that way you could observe one trace and compare it to the entire history of all your other traces very efficiently. They took a pretty simple interpretation of genetic algorithms, really only applying random mutation and occasionally a crossover between a previously known good input and that got new code coverage and the next one. They used a context-free grammar to describe the input rather than just doing simple byte flipping. And so they were able to actually mutate the grammar itself and then use the grammar to generate new inputs that match the now modified grammar. And then the only real weakness is that they didn't have a well-engineered tracing engine that was very efficient. So the actual genetic algorithm side, the evolutionary testing side, was pretty sound, but they didn't have a quick way to apply this where you could actually use it in practice the way that we do today, because it takes millions of iterations to really shake out good bugs and fuzzing. Their major contributions were certainly, first of all, actually taking genetic algorithms, applying them to fuzzing directly, and talking about it publicly to kind of put that seed into the community for further research. And the fact that they used the Markov process was an efficient data structure to store an entire history of traces rather than having to go and parse like a binary format or a list of addresses that you executed each time and do diffs over that. Using a Markov process, you keep that kind of state all in one data structure. And so this system also allowed them to select target locations, code locations ahead of time, which you do by adding weights to the graph, right? So in this case, what you're looking for is unique paths typically. So you want to find the exceptional path, the one that's not taken by all the inputs. When you find your bugs, they tend to be in less traveled code. And so by weighting the path in a way that says, if this input reached a transition on the graph that was rare, then this is probably a better input than one that only reaches transitions on the graph that are common. And so in addition to be able to holding the entire history of all of your inputs doing it this way, you can also specifically point out parts of the graph and weight them in a way that you want. So you can drive the feedback algorithm directly, which is nice. Something that you can't do with current storage. So the main problems with them were that they had never open sourced it or really discussed much about the internal architecture other than one deck of slides. And it's too bad because a lot of the ideas, I think they were off to a great start and they were really just missing a good tracing engine. Because the next year we had a talk from Jared DeMott, and he was doing his PhD on evolutionary testing, and unfortunately I feel as though he kind of took it to an extreme, trying to track too many variables, getting too close to the biology of things rather than remembering that we're trying to come up with just an efficient signal to let us determine whether or not the execution that just occurred was useful or not. And that led to him creating a system that was both slow due to the tracing mechanism of BTF for the debugger API, as well as a bit clunky because he was storing a lot of state in a database. So you had to query a database every time and do, you were comparing your current iteration to all other iterations through SQL queries. And as we know, that's just not the fastest way to go. And he had just a larger concept of genetic algorithms as applied to testing that didn't really pan out that well. He did experiment with doing hooking at a function level and trying to use that in evolutionary testing, and it worked somewhat in his specific examples, but he was only really looking at text mode protocols, which generally speaking, when you architect software, I think that you're more likely to have a dedicated function per verb in a textual grammar protocol than you are if you have a dense packed structure that you're going to be tearing apart and have a lot of logic in a particular type of format. So I think since 2007, we've discovered that block-based granularity is the better one to go with. And then, of course, what I would say has kind of been a new evolution in the last 2 to 3 years is a real practical, well-engineered tool that is designed to be idiot-proof right out of the box and kind of be a mutational fuzzer just like any other mutational fuzzer, except that it has a lot more logic and intelligence to it. Most mutational fuzzers don't take a lot of setup or reasoning or configurations or twiddling with variables or figuring out weights on a Markov graph. They just kind of are fire and forget. And so Amercian Fuzzy Lop has pretty much pulled off that goal. And what it does is it uses a compile time instrumentation out of the box, which when you compile your code at every logic branch within your code, so every if-then statement, it injects a callback function or injects a couple of instructions, which essentially update a byte map that contains the state of this current trace, as well as it makes it comparable to all previous traces. So basically what this looks like is there's 64K in memory, and this is a byte map that allows you to increment offsets into that to indicate number of times you visited a branch. The way that you determine what the offset into that byte map is you take your previous block ID and your current block ID, you XOR them together, and then modulus 64K, that's the offset into the byte map, and you increase it every time you take a branch at that offset. And so basically what it lets you do is very, very efficiently, with just a couple of instructions, encode an edge transition just by using a byte array. And then you can also keep this byte array, keep appending the current bytes in this array to a total historical, like a global array that shows your entire corpus coverage, essentially. And so, and he also took a comprehensive approach at mutation fuzzing strategies that we've seen kind of spike started, I suppose, encoding specific mutation strategies that weren't just random bit flips at a percentage, but they were more like, edge values for integers or format strings or various other inputs that we know to be good sets for doing mutation with. So in general, in its dumb mode, it's already just a good mutational fuzzer, and then it adds this feedback mechanism through a compiler plugin that tracks the code coverage via these edge transitions that are encoded into a byte map. And ultimately, it's the first practical high-performance guided fuzzer that's available to the public. So, and it even comes with a nice little GUI. You can kind of see up here. It's got a little nice old-school ANSI style looking layout. It also gives you a global coverage map. It allows you to use tools to do min-set on the corpus. It allows you to minimize individual inputs. It comes with a lot of extra tooling. It also includes a fork server, which reduces the initialization time every iteration of the process. So once you get the process launched, it just forks it every time, which in Linux is a copy on write. And last year, in my talk, we kind of were exploring, we ported AFL to Sidewinder environment, which simply required implementing some shared memory APIs. And then also, we tried to write a Windows native fork, which was successful using NT clone user process. However, when you create processes using that low-level system call, user32 and the CSRSS subsystem's not aware of it, and so you're limited to fuzzing. Essentially, you're limited to fuzzing code that you compile yourself, because in Windows, almost everything is linked to user32. So turns out that wasn't exactly the best approach in the end, which is why I got interested in looking at other tracing engines and Intel PT and things like that. So, but Amercian Fuzzy Lop certainly has added a lot. It's had a ton of contributions. The persistent mode fuzzing is another one where essentially you can add annotations to a function and it will be able to restart at the beginning of a function, and you give it a little cleanup logic as well. And so it'll launch the program and just do in-memory fuzzing essentially, which there hasn't been very many tools out there that are just kind of ready to go to do that prior to AFL. In the last 2 years, we've seen LLVM come out with libfuzzer, and we've seen some other things that accomplish the same goals, but Amercian Fuzzy Lop really did guide the way in that direction. And also, the last thing I'll comment here, some of the things that Ben Nagy has been doing talks on, he mentioned using reuse of inputs that were generated through directed fuzzing like this, which is very, very useful. So for example, if you want to target a binary program and you don't have a way to efficiently instrument it, you can use a reference implementation or an open source implementation of that same parser and generate all your inputs. This will save every unique file that went somewhere interesting or unique on the graph. So every input will be exploring a new part of the graph of your target under test, meaning that it probably has new features or it exercises loops longer, or it's doing something interesting. And so each one of those inputs is saved for you, and then you can go reapply those inputs to any other parser of that format. And a lot of fuzzers actually don't do that, even other guided ones. Some of them only, when you're doing evolutionary testing, the fitness function leads to what's called the elite sample, and oftentimes they get rid of all the other ones. Amercian Fuzzy Lop keeps them all for you. So the observations here is if you're going to write, well, number one, Amercian Fuzzy Lop is a pain in the ass to actually hack on yourself. It's not a modularly written system or anything like that. So, if you want to write your own fuzzer and take some attributes from it, obviously keep it simple, stupid actually still does apply to fuzzing, even when you're getting into more technical approaches to it. Performance does need to be a priority. I mean, it's a first-class function of finding bugs if you're going to use mutation. The more iterations you can do a second, the more likely it is that you're going to stumble upon that input that will actually lead to a crash. And so source instrumentation really can't be beat. There's a lot of reasons that it's more performant than doing dynamic binary instrumentation or any other type of tracing. But obviously, there's a lot of software out there that we can't apply that source instrumentation to because we don't have the code. And so we'll talk about some engines that we worked on that kind of augment that so you can do binary stuff. But it's simple to use, finds tons of bugs. It actually fostered a user community because it was efficient and because he did a good job of kind of keeping track of a bunch of high-profile bugs. And I guess being at Google, they were able to scale it up a bit and actually apply it significantly and find a whole bunch of stuff. And last year, when shell shock was happening, as soon as shell shock kind of hit the web, he found 4 or 5 different variants within, I think, a couple hours or a day or something. So it's pretty cool if you actually have an idea of an area code that you think is weak anyways. You can take a trigger for a previous vuln that's been patched and kind of let it go, and it will explore areas around that as well because of the feedback mechanism. I would call Amercian Fuzzy Lop the current state of the art for mutational fuzzing and feedback fuzzing. There are new tools that are coming out. honggfuzz just added guided fuzzing last year as well. If you're not familiar with honggfuzz, it's another Linux or POSIX portable fuzzing engine. It's previously was pretty much just a mutation engine. It's from Robert Swiecki out of Google as well. But he added wrappers to interact with the Linux perf subsystem, which itself wraps all kinds of hardware counter-oriented feedback, as well as now it has wrappers for doing BTS and Intel PT, which we'll get into later. And also, this was an example of one of those fuzzers that added some logic for doing tracing and feedback, but he didn't keep an entire corpus. He recently added a bloom filter to determine whether or not he's generated that input before, so it kind of skips some of the cost. But the nice thing about it is that it can operate both in a binary mode as well as a compiler instrumentation mode, and it works pretty much everywhere that has some form of POSIX support. The latest fuzzer that's kind of in the guided fuzzing direction is Choronzon, which was discussed at Zero Nights last year from ArgP, I believe, and some of those guys. And I would say the main benefit to this one is that it adds some serialization capabilities and some knowledge about not specific data structures in a format, but general structure like container formats. Is this a block-based type of format, or is this a file system type of format like OLE structured storage, or is it hierarchical and things like that. Unfortunately, he just uses off-the-shelf tracing engines, so he used Cosink's run tracer, I believe, and then he used Dynamo Rio's code coverage tracer, which is actually a hit tracer in its default mode. So some of the logic for keeping around the feedback is a little bit weaker, but some of the upfront, like serialization and being able to tear apart an input and actually get deeper into it to fuzz it is engineered a bit better. And then there's all kinds of other guys that have done similar things. AutoDafe was probably one of the earliest fuzzers that tried to add in some memory tagging, so you kind of had a concept of whether or not you may have tainted this specific API. Jackson Corret made the blind code coverage fuzzer that came out a couple years ago, and honggfuzz is kind of a miniature clone of AFL. But so the whole point of kind of doing that little review is, what are the attributes that we want to pay attention to if we're going to write our own fuzzing engines? Number one, guided fuzzing does find more bugs than blind mutational fuzzing. To do guided fuzzing, you need a fast tracing engine with block-based granularity. And not only that, you need a fast logging mechanism so that you're not diffing lists of basic blocks. You need a way to store in data, a very efficient method to compare a current run against the history of all other runs. And that's pretty much what AFL and Sidewinder had contributed. And then I learned from Jared DeMott not to get overly complicated in designing and adopting your evolutionary testing. Try to keep it as minimal and as efficient as possible so that for the amount of data that you're recording and dealing with, you're getting the most efficiency of return so that you can continue to find bugs as quickly as possible. So, and then the other things that we would like to see is, portable code. Almost all this stuff is written for Linux. Very few people set out for some reason to write an evolutionary testing fuzzer for Windows. So we're working in that direction. And, just idiot-proof stuff, helper tools, which you can pretty much use already anyways, and the grammar detection type stuff that Choronzon has added. So let's talk about binary translation, because this is a fun topic I enjoy. So binary translation is essentially a JIT for native ISOs. And it's actually been applied across ISO before, back when there was big iron Unix. But modern times, you pretty much see x86 to x86 JIT. And in rare cases, you'll see x86 to x64 JIT that uses the extra register space to do things like memory tracing. Matthias Player has some stuff like that. But in general, what you're doing is you have a custom loader. So you replace the Linux linker with a preloader that loads the binary in itself. And as it loads it, it's able to, as it discovers code, when you execute it, it copies it into a code cache. And as it copies it into the code cache, various DBI engines allow you to instrument that code and insert either callbacks or instructions directly. And then it links these blocks into what they call traces, which is essentially a series of basic blocks that are executed within the structure of a graph. Like if you have a back edge, then that begins a new trace, the destination of a back edge. Or if you have a call, a far branch, then that begins the execution of a trace. But if you have a series of branches that are executed, in a larger graph structure, then that will be an individual trace. It's kind of like a single path throughout a larger function, right? So all the performance comes from the way that they load the code into its cache and how they generate these traces. Originally, the whole point of doing the trace generation is to determine which paths are executed the most commonly, and then try to optimize how those are arranged in memory so that they're more attuned to the native requirements of your hardware, like your L2 cache, and to avoid things like branch misses and keep your TLB. Like if you're executing the same trace over and over and over in a loop, then you want that all to be resident and not spread out in the code. And then so this originally came out of HP, and then some work was done at MIT to expand on it. And those guys started a company called Determina, and now they're at VMware, and that's how we ended up with open source Dynamo Rio. On the pin side, that was the Intel guys obviously doing something similar. And there's ongoing work in this space right now. There's still papers and patents and research happening, especially at VMware. The advantages of binary translation is that it tends to be supported on most mainstream OSs. You could pick, Pin or Dynamo Rio or Frida and run them on Windows, Linux, OS X, maybe some BSDs. And they're faster than the traditional hardware tracing mechanisms, because until recently, the cost of adding special functionality into a processor seemed to exceed the need for doing good diagnostics. So a lot of the tracing engines that were available were slow or clunky and not really efficient enough for doing online testing like we want to do. And then they can easily be targeted at certain parts of code. You're working in software, so it's just much easier to turn on and off the tracing functionality. They have built-in hooking engines, so you can hook certain APIs and delay enabling your trace, things like that, as opposed to programming low-level hardware interrupts and MSRs. But of course, they do incur a performance overhead, and this is mostly architecturally, because this loader that gets added in there, the thing that's copying the code from the native map into the code cache that's actually executable, that is essentially a whole extra layer of context switching. And due to that fact, it essentially, rather than just have a context switch that goes whenever you need I/O resources, now every time you discover a new piece of code, you're getting a context switch. And this incurs a high cost because, again, code locality, this code is unlikely to be directly in your cache already, and so you end up getting a fairly massive overhead due to that. Also, just as a thing that I've observed, the ISA compatibility is not guaranteed, right? So we would assume that maybe Pin would be pretty darn close to what's actually in the silicon for Intel, because that's using the Z disassembler on the back end. But we have no guarantee that it's supporting the latest feature sets. And we certainly don't have any guarantee that Dynamo Rio or Dynast or any of the other engines are at one-to-one parity with the native ISA. So if the tracing that you're doing needs to be exactly precise to what the hardware is doing, then you might run into some pitfalls using a software-based translation engine. And then also if you're doing tracing like in the malware realm as opposed to just doing fuzzing, if you're up against hostile binaries, then these are easily detectable, essentially. Just like virtualization of any form, there's kind of key giveaways of either certain memory maps not being available or other things that are anomalous to a normal operating system. So I'm not really going to talk about Valgrind other than VexIR is really useful. And if you've seen tools written on Valgrind like Memcache and other crash analysis tools, a lot of that functionality is now available in Dynamo Rio, which is at least twice as fast, and it's portable across operating systems. They include things like the ability to do shadow stacks and memory tainting and things like that, all in Dr. Memory, which is an advanced debugging tool built on top of Dynamo Rio. So my main reference point for Valgrind is that it's awesome. It's just kind of older and slower, and a lot of people have access to it in academia as they may go through some systems engineering classes. But I would like to see people move towards something that's at least portable, because all the tooling written on Valgrind is not portable to Windows. So that's the more significant tools that have been written on top of Valgrind, though, are Memgrind and Flare. Flare is really cool. That's one of the Choronzon being able to kind of tear apart components of an input reminds me of Flare. And Flare essentially was a method for hooking deep into a program to allow you to fuzz beyond things like checksums and compression and get to the guts of the code. That was also worked on by Tavis Ormandy and Will Drury. So Pin is probably, can I get a raise of hands? Has anybody used Pin before? Yeah, so it's probably going to be the most commonly used one today. I call it DBT with training wheels. A lot of people migrate towards it because it has a higher level API. It's written in C++. It's really easy to get into. I mean, in my next slide I'll show you in 5 lines you have a callback to whatever you want to do in any basic block in your target. But unfortunately, there's a few things about the design of pin that reduce the efficiency. Like number one, you don't get to observe a basic block when it's loaded into the cache. You observe basic blocks as they're executed out of traces. And this is significant because traces can contain multiple basic blocks, meaning that you can re-instrument the same block over and over and over if multiple traces are being generated that include that basic block. That hook will only be in that trace, so it won't persist. So each time it has to rehook it. So that's kind of slow. Another problem is it's closed source and licensing is pretty restrictive on it. You can't just distribute pin with your tool. But in general, it's just really easy to get into. So like, for example, this is all you need to write besides a couple of init callback functions. Or like, this is the callback function. There's a couple of initialization APIs you have to call, but this right here will allow you to insert a call anywhere in a basic block that will call back to your basic block hook, and then you can do whatever logic you want. You can observe and analyze the program. I don't know why my font is rendering weird. I'll blame LibreOffice. But so basically, pin is just really easy to get into, but it's not very fast. It's quite a bit slower. And in fact, I do have some demos of each one of these tracing engines here, which I will show you really quick what we're looking at. So I have a demo that shows a block trace using pin. We're going to run libpng over a set of 100 inputs and just see the time that takes here. And it will take roughly 60 seconds or so. But all we're doing is we're running the default libpng PNG test functionality, which just kind of parses these PNG files real rapidly. And essentially, the reason that pin is slightly slower is that it's not able to inline your functions directly. In theory, if you don't have any conditionals in your analysis function, it will inline them. In practice, I think that it's very conservative in doing that. So it doesn't allow you to do interleaving of instructions. It doesn't allow you to do register liveness checks and actually instrument the AST. It's more or less just doing callbacks out to your hook function. So this should be about done here. But you'll visually be able to see the difference between this and the next demo anyway. So I'll just cut it short so we don't go over. So Dynamo Rio is essentially a much deeper introspection on a DBT. It allows you to directly modify the AST that's inside the instrumentation engine. So when it loads your binary and it discovers a new basic block, it converts that block into an AST internally, and then it allows you to actually do checks on the registers, the flags, like everything you want to do. You can synthesize instructions on the fly. It's also portable and BSD licensed, so if you're writing tooling that you want to be able to ship and package, it's available. And it has powerful tools like Dr. Memory, which, like I mentioned already, has shadow memory, taint tracking, all kinds of stuff similar to Valgrind memcheck. It does take a little bit more effort to read this font. No, it takes a little more effort to do the instrumentation. What this is doing right here is essentially it's saying that we want to insert some instructions into each basic block. We don't really care where the instructions are at, as long as we are able to put them in sequence, and we're looking to see if flags are dead because we're going to do an increment which will impact E flags, and we don't want to have to store that and restore it. So it's looking for a point in the code where our injected instructions are going to not have to do a whole store and restore of previously saved data or registers, which will greatly increase the efficiency of your instrumentation. So it takes a little bit longer. This is the first part of the function. That's the second part of the function. And I'm going to open source a tool that actually is a full-fledged block tracer for you. I can show you an example of this one too. It's like visually much faster. Okay. So this is the same exact test. As you can see, it's much, much faster. It's literally not doing anything else other than being more observant about where it's adding its hooks in, and it's in line. Functionally, it's doing the exact same amount of work, and it's obviously, this one took 11 seconds, the other one took over a minute. So just by using the right platform and doing just slightly more work on the front end, you can have a much faster tracing engine. But that's not all. We have Dynast next, I believe. Yeah, so Dynast is a really cool platform. It comes out of, University of Wisconsin, Madison, and University of Maryland. Actually, Barton Miller is the head of the research group behind it, who coined the term fuzzing to begin with. So that's kind of cool, just a coincidence there. But basically, it's the only open source platform that allows you to do static binary rewriting, as opposed to only being able to do runtime-based hooking and injection. And this is really critical. Once again, it all has to do with code cache and code locality. But by being able to rewrite your instrumented binary back to disk, the operating system's advantages of doing things like copy on write when you fork, and being able to have all the code serialized into one blob of data rather than having it being dispersed and allocated on the heap and not be local in its cache makes a massive, massive difference. It's a little bit harder to write tooling for. It does have an online mode that only allows you to do callbacks. It has a whole bunch of APIs. Like before, my tagline for this was, it was the kitchen sink of dynamic instrumentation. But really the most novel thing is that it allows you to do static rewriting. And we use this all the time. And when we test commercial software that has binaries available on Linux, this is our go-to tool. And we released a plugin for AFL directly that allows you to use Dynast. So you just rewrite the target binary once, write it to disk, and then you can use it with AFL. And it has only about a 30% overhead. So if you've used the QEMU plugin, or the QEMU binary trace mode for AFL, it has a really significant overhead. Dynast is actually super, super performant. And we'll show you, oh yeah, and of course, building Dynast is NP hard, so don't try it yourself. There's like a whole bunch of dependencies, and you have to like figure out which ones should come from the vendor, which one you should compile yourself. It's a pain in the ass. But I uploaded a Docker file, so you can just either run it in Docker or copy out the instructions for yourself. To write the plugin, they have a number of APIs. This one is the binary patch API. And you essentially just iteratively walk the graph, find your blocks, and so on. You can reference this code later. It'll be available. Let me go ahead and show you a demo of that one. So that last one was 11 seconds. We expect this one to be even faster. Oh, there it goes, just 1 second. So we went from like over a minute if you write the tool in Pin, and if you choose to write the tool in Dynast and you are able to run it on Linux against dynamically linked software, then you don't even need source code it. It's obviously way, way faster. So 60 times speed up just by choosing the right platform and doing a little bit of extra work up front in the code that you write. So my recommendation is, if you're going to be writing tracing tools, pick the right platform for the job. Don't necessarily just go with the easiest one because it's approachable. So if you're going to use dynamic binary translation, the tips that I can give you is that, first of all, you only need to instrument indirect branches. There's no real point in instrumenting direct branches, so that's an easy cost savings. You can delay instrumentation until the input is seen. If you're using this for fuzzing, we typically know that we're either have a file or network-based input. You can delay until that occurs. So if you can't isolate a library, or you don't have a lightweight console application wrapping the logic, then you can at least wait until the program is initialized before you actually go into your heavyweight tracing. You can also limit to the threads that access the data. If you're targeting a larger application, typically one thread will be the one that's reading in the data and parsing it into data structures and then handing it back to the other threads. So you can isolate that. Some of the APIs have if-then-else logic built in statically, which will handle inside their code cache a much more efficient way rather than putting conditional logic in your analysis itself. Avoid the trampolines. They're very, very slow compared to being able to serialize and synthesize instructions directly into a block. And inject a fork server if you're repeatedly executing it. We have a tool which I call TurboTrace. It's actually not on GitHub yet, I don't think, but it's generic. If you have a corpus that you're executing the same tool over iteratively, it injects a fork server and gives you about a 30% speed boost as well. I demoed that last year. So let's get into the hardware tracing section. I don't know how I'm doing on time. Okay. Shoot. So essentially, CPUs come with hardware tracing. They have a performance monitoring unit. It exposes things like counters and sampling and things like that. There's a guy at Intel that wrote this PMU tools toolkit. It's cool to experiment with. I'll just leave that to the user because I'd like to get to some of the more important stuff. When you program a CPU, when you enable hardware tracing modes, essentially what you're doing is you're going to be configuring model-specific registers. These are registers that are not exposed to you in user land. These are only available in CPL0, root kernel mode, rather. And they're entire instruction sets that are designed to turn on and off special feature sets that are in the CPU. When you program them, essentially what you're doing is you're setting up interrupts so that the CPU can notify you when events occur after you've set these flags and bits, maybe given it pointers to buffers and so on. You set up an ISR so that it can tell you, okay, your buffer is full. Now you might want to copy this from your kernel driver into user space and so on. I'm going to kind of briefly go over some of the basic stuff here, let you reference it later because I do want to get into the newer stuff before I run out of time. Single stepping, we all know it, slow. Branch trace flag is just a mode of single stepping that steps on the branches. Reference K2's talk from CanSec if you want to know more about that. There is a specific MSR register that has a number of flags that you see here. Each one of these enables different types of tracing modes that were kind of the traditional. So on the top you have the LBR, which I'll show you a diagram of, the branch trace flag, branch trace store, which is the cache for doing branch tracing in the old mode. Branch trace store essentially allowed you to pass a structure that says, here's the base of my buffer, how big it can be, whenever I want to be interrupted to be told that it's full. And essentially the CPU would store this DS area record structure, which includes your IP address, all of your registers, context, and things like that, the flags and so on. So essentially every time you took a branch, it would be able to dump context into a buffer for you. Graphically, it looks kind of like this in the instruction pipeline. I ripped this slide off of somebody else, but it is a nice illustration. Essentially, when your branches like a ret or a jump are loaded into the instruction pipeline, there's a series of registers behind the scenes that you don't normally view called the LBR registers. Those keep the branch from and to, and also a bit on whether or not that was a predicted branch or not, just for internal cache tuning. And if you have the branch trace message flag enabled, then that will actually go outside of the CPU onto the system bus and into your L2 cache. Your L2 cache will then hold a structure that will point to the save area for the storage. And essentially, you'll just get a series of these structures, which are your context at the time of your branch. Unfortunately, it's really, really slow. I've got a demo of that, but it's super slow. It's not really worth going much further into. And I'll let you reference these slides later as well. So Intel Processor Trace is the new hotness. It was available as of last 2 years pretty much in consumer devices. It's not on the server side yet. They're still in Haswell. But soon they'll be catching up, and they're going to get all kinds of great features like SGX and Intel PT, and apparently this new Intel CET stuff, all super exciting. What you need to know about Intel Processor Trace is that it is the first efficiently engineered tracing engine to go into an Intel CPU. It's per core. It gives you essentially full system tracing all the way from SMM all the way up to user space. And if you want to toy with it, the easiest way is now in Linux 4.1, which is after I started developing this stuff last year. They have added some support to the perf subsystem. There's also a simple reference driver called Simple PT that the same guy that wrote the PMU tools has up on GitHub. And there's some support in Intel vTune System Studio, but it only allows you to do it in remote, like slave debug mode, which doesn't make a lot of sense to me. And then as of today, we have a working Windows local host hardware supported tracing engine. So as I mentioned, it can actually trace down into SMM if you have a digital certificate, so most of us won't have that access. But it is able to trace hypervisors and kernels and user space and do filtering based upon the CR3 page table of your choosing. It logs directly to physical memory through a linear address range, and it can also take not just a contiguous address range, but in Skylake they added the ability to give it an array of pages or array of ranges, so you're able to have arbitrarily large linear cache that doesn't have to be contiguous, which can be difficult to allocate. One of the main features is, again, it has a minimal log format, and this echoes what I was saying about when you do the directed fuzzing. You need to figure out ways to keep these traces small so that you're not wasting time in I/O instead of actually doing what you want to do. So, for example, they can do 1 bit per conditional branch, and they can actually stack up to 6 of those in a single packet, like a protobuf kind of packet. So what this means is essentially if you're in a loop, for example, and you're waiting for your counter to count down, it can tightly compress the number of times that branch was taken or not. For indirect branches, it also, of course, has to record the destination address. It interrupts the source and destination for logging, and the main problem or the main difficulty or hurdle with this is that you need access to the original memory map information to decode the trace because it's so sparse. So this is kind of what the format looks like. Each of the top ones are individual packet types, and these tend to be literally like just a couple of bits. So I'll show you a decoding of that in a second. I can't tell you how much of a pain in the ass it is to get this configured. It's 90 pages in the Intel software developer manuals, so we can't just randomly flip bits to get this to go. You really got to know what you're doing and figure out which feature sets you want enabled. This isn't really meant for you to read right now. You can look at it later. But basically the idea is that per CPU, you can enable these MSR registers, and then it will write this heavily compressed format out to your linear cache, and then you can register an interrupt to handle when that cache is full, or you can use it in ring buffer mode and then dump it later when the process exits. If you want to toy with it, you can use it through the Linux perf subsystem. If you want to write tools around it, I actually recommend either Simple PT on Linux or our new Talos Intel PT driver. I have some of the structures in here, but we're going to publish the code next week anyway, so you guys can just go through the code since I'm a little short on time. But the idea is that, per processor, we have a trace buffer, and each one of those buffers gets allocated via allocate physical memory in Windows. Allows you to filter on each core, and then a whole bunch of configurations for which features you want to enable. This is more or less directly right out of the manual, and so on. So let me just show you, see if we can't get a demo here. So here's what we should be expecting is loading a driver, and then we're going to run a program under trace, and then we're going to use the reference libipt, which knows how to decode this packet format to dump out these records. So right here, these are those internal packets that I just showed you in that image. These can be mapped then later on to a process map, and so essentially you can end up with a series of blocks that were executed. So let's see if the demo gods will be with us today. And once again, all this code, I have implementations of every engine that I've talked about today. All this code will be open source and up on GitHub in the coming week or two. I go directly from here to HushCon East, and so after I get back from that, I'll just do a final tuning and upload them for you. So are we live? Yes, okay. So we have we're going to go ahead and use the driver installer here on the Windows PT driver. And so this is just a driver that needs to be a driver or in a hypervisor just so that you have access to program the MSR registers directly. This is doing all the heavy lifting of configuring all the flags and setting up the buffers and allocating the physical address ranges so that they won't get trampled on by anything else. So now we are installed. Next we want to go ahead and this is just our little test driver. What this does is it launches an application, suspends it, gets its CR3 value, and then tells the Intel PT driver to start tracing for that. So this is our little test here. We'll go ahead and exit, so that will copy we do a 0 copy from the physical address up to user space for the file. And then over here, we can do a dump of that new log file. And here it is decoding the packets, and these were, I guess it's good. Let me pause it so you guys can actually see what we're seeing here. So we're seeing here in the top, so I guess the font's kind of small, but at the very top you see some unique packets that are essentially telling the CPU what mode to enter into and to enable the Intel PT trace driving. And then you'll see we have some of these packets that say TNT, that's taken, not taken, and then it has a number after it for the number of branches that are represented there, exclamation marks meaning that it was taken, the dots meaning that's the 0, it's not taken. And then below that you'll see like the TIP packets, that's the taken IP or the target IP address, and so on. So that's the working Intel PT on Windows, and this will all be available to you soon. And as far as conclusions, essentially, I know it's not everybody's favorite hobby like mine to write tracing engines and so on. So I think ultimately people should try to engineer tooling on top of tracing engines that fit what their needs are. And I'm releasing this code, and I want to support it in Dynamo Rio, Dynast, and Intel PT engines. So if you have an application that you need a tracing engine for, I would like to hear from you, and we can work together to increase the efficiency of tracing engines for security testing overall. And that's it. So thank you very much. We might have time for 1 or 2 questions. Is it 1 or 2? Sam says we can have 1 or 2 questions. No questions? All right, well, thank you.